So for the start of Unit 3, we are still in the topic of probability like we left from Unit 2 or Chapter 4. So at Section 1 of Chapter 5, we look at constructing a probability distribution from a random variable. And we also discuss, what is a probability distribution for a discrete random variable. So let's look at a random variable is just any variable who's determined by chance. And there's two different types of random variables we discuss in Unit 3. In Chapter 5, we only look at discrete random variables. And so from a previous unit, I believe Unit 1, we talked about what a discrete value was, and that's any variable or any value that can be counted and has a finite number of possible values. And a continuous random variable we'll talk about in Chapter 6 is any variable that can be measured rather than counted. And this is kind of just a little review of, we had broken down all data, all numeric data, or all data as either qualitative or quantitative, and then quantitative data can be discrete or continuous. So kind of just to bring that back from your memory from what we talked about previously. But for this chapter, we look at discrete random variables, situations that involved something that can be more or less counted, not really measurable, has a finite number of values, and then continuous random variables we'll look at in Chapter 6. So for a probability distribution, we look at two requirements, and these two requirements we actually spoke about in Chapter 4 when we talked about probability rules. The first requirement for a probability distribution is that the sum of the probabilities equals 1. And the second requirement is that each individual probability for the event that we look at is between 0 and 1. So these two requirements are what we previously looked at in Chapter 4. But now we're applying those requirements to a discrete probability distribution. And so let's look at a few examples here about what a discrete probability distribution looks like. So here we have a probability table where when we think about a table, we think of X and Y are independent and dependent. In this particular table, the top row of the table represents our event X. And so in this case, the event has 4 possible outcomes, which is the number of heads. So it could be no heads, could be 1 head, could be 2 heads, or 3 heads. And the lower row of the table, which customarily is the dependent variable, or Y, doesn't represent that here. It represents the probability of these outcomes. So in the situation, more than likely was flipping a coin a number of times. That part we don't have, but just so you can kind of get an image here, this table represents a discrete probability distribution because of the two conditions previously stated. The sum of the probabilities is 1. So if I take each one of these probabilities, so the likeliness of getting no heads is a 1 out of 8 chance. The likeliness of getting 1 head is 3 out of 8 chance, and then so on. So if I add those together, I get 1. The second requirement is that each of those probabilities individually, so each one of these values is between 0 and 1. So as long as those two conditions are met, then we can say that it represents a probability distribution. Now we can also represent a probability distribution graphically like we did in Unit 1 with the histograms. The difference is that this is not a frequency. It's more or less like a relative frequency because it's represented as a fraction or as a percentage or as a decimal, So we could represent this as a decimal approximation instead of the fraction. And the horizontal axis is not a class limit or a boundary. It's the event that we're interested in. We can even describe the shape of our probability distribution. So if we look at this histogram-like distribution, it appears to be approximately symmetrical. We kind of draw like a line down the middle. It's the same on each side. So we can comment on the shape of this distribution. We can just say that this particular probability distribution appears to be symmetrical due to its shape. Now, for these four problems, we want to determine whether the distribution represents a probability distribution and then explain why it doesn't. So in order to do that, we look at those two conditions of the two requirements. So the first condition, the sum of the probabilities is equal to 1. So those are all the values in the bottom row of each table. And the probabilities themselves are between 0 and 1. So when we want to determine if a probability distribution, if we want to determine if these are probability distributions, we mainly look at the probability values to determine that outcome. We're not really concerned right now with the values of x because this is discrete. These represent a finite value. We just don't know what the values represent right now, which is okay. We're just mainly focused on the probability values right now. So for this first table, if we add these three values together, we will get 1. So that checks out. However, for the second condition, one of the values is negative. So that doesn't, you can't have a negative 40% chance of something happening. So that doesn't fall in line with that second condition. So this would not be a probability distribution. So for the second one, again, if we add all those values together, we will get 1. So that checks out. And each one of those values are between 0 and 1. So this would be a probability distribution. And we look at the third one, we can add all those together. 8 equals 1, that checks out. Each one of the values is between 0 and 1, so that also checks out. So this is also a probability distribution based on those two requirements. And for the fourth one, the first condition does not check out, because if we add these together, we get a value greater than 1. But the second condition does work, because each value is between 0 and 1, or it can include 1, so each of these could have been 0, and that could be 1, and that still checks out. But ultimately, both conditions have to be met for this to be a probability distribution, and they're not. So two of the distributions are not probability distributions, 1 and 4, and 2 of them are probability distributions. So in your homework for section 5.1, the only thing you'll be expected to really do is, can you tell the difference between a probability distribution and something that's not a probability distribution? Those would be the two things you'd be expected to do in your homework. Now, what I would like to do also is kind of talk about how we construct a probability distribution with this example. You won't have to construct one in 5.1, but you will construct one in section 2. It'd be kind of nice for you going into the section having a little bit of an understanding of how we approach constructing a probability distribution. So first says the first 4 triangular numbers 1, 3, 6, and 10 are printed 1 each on one side of a card. The cards are placed face down and mixed. Choose 2 cards at random. Let x be the sum of the 2 numbers. Construct the probability distribution for the random variable x. So we're being given instructions on what x represents. So we think about, well, x is the sum of 2 cards drawn at random. So in our mind, we kind of have an image of what the values of x can take on. And again, that's discrete, right? It's countable. It has a finite number of possibilities. So this is definitely something that represents a discrete situation. So what we need to determine is how can we find the value of x, and then how can we find the probability of that value? Because that is what will help us construct our probability distribution. So for this, I thought it'd be really good to kind of reiterate or incorporate the tree diagram that we talked about previously, because we need to know our sample space to find the probability. So to do that, think about the first card, right? There's only 4 cards because it says each one of these numbers is printed on one side of a card and they're laying face down. So we're choosing 2 cards at random. That means the first card we choose can be any one of those 4 numbers. It could be a 1, a 3, a 6, or a 10. The second card that I pick is based on the first card I picked. So we have a dependent relationship here. If I choose the card number 1 first, that means I can only choose a 3, a 6, or a 10. So if I chose a 1 and then a 3, or a 1 and then a 6, or a 1 and then a 10, that means the sum would be 4, 7, or 11 if I add those together. So those are my first three outcomes if I choose a 1 first. So then if I choose a 3 first, then my outcomes would be 1, 6, and 10. And so the sum would be 4, 9, and 13. Right? If I do 3 plus 1 is 4, 3 plus 6 is 9, 3 plus 10 is 13. And I keep this process going until I have all the possible outcomes, which is the sum of the two numbers on the cards that I chose, because that's X represents the sum. So this would be my sample space, which is the number of outcomes. So I kind of keep that process going, and these 12 values represent my sample space. So what we want to determine now is when we construct our probability distribution, what are all the possible values of X? So X could be the number 4, and there are only 2 4s. And so we think about probability. So the probability that I get a 4 as a sum would be only these 2 outcomes out of the 12, so 2 12ths. And then I could also get a sum of a 7. Well, the likeliness of me getting a sum of a 7 is also 2 out of 12. I could get a sum of a 9, so that's also 2 out of 12. I can get a sum of 11, that's 2 out of 12. I can get a sum of 13, 2 out of 12, and then 16, 2 out of 12. So this is my probability distribution, and there's only 6 possible outcomes because of the duplicates or the repeats, but there's different ways to get those 6 outcomes represented by the probability. Now, we always want to reduce the probability, so really, I could make my probability distribution like this, where I have a 1 in 6 chance of getting each of these different values. And I can take that information and I can describe the shape, like we described the shape in kind of that example with the number of heads. Because all the probabilities are the same, the distribution is more uniform, and uniform just means they have the same height. So if I were to draw out a histogram, this is how my probability distribution will look. Each of these sums have an equal likely chance of being chosen. So I can get any one of these values as a sum just by drawing 2 cards at random.